Okay, good morning. Mic check. Okay, I think we're all good. Hope everyone's doing well. So we are in morning, Tyler. Morning, Captain Price. I haven't looked to see who else is out there, but good morning to everybody who's out there. Hello to you if you're watching the video later. All right, so we're in week 13. Moving right along. Let me just show you kind of what's going on. So next week is Thanksgiving week, but at Butte College, we only take the Thursday and the Friday off. So just be aware that if you're taking other classes, that they may be on their normal routine. In our class, in week 14, I'm calling it a review week. So for those of you who are taking two classes with me, that might ease up the pressure on you a little bit. But just a heads up about next week for this class, CSCI 10, Computer Architecture and Organization. The routine is a little bit different because there's no assignments. I will be online on Monday morning, and I will do lecture. I will do some review, but I will also, the whole lecture really is review and getting you hopefully well along your way toward your start toward the second individual project. So it says review next week, but the way we're going to review is we're going to look at all of the tools and techniques we have in our toolkit to solve individual project 2. So that's going to be the goal next week. So if you want help getting a good kickstart, then hopefully you will either be able to be there and get it live and interact with me, or you can watch it on the video later. So that's for this class, week 14, and I'll show you when we go look at the modules. It's slightly different next week because for this class, CSCI 10, we're not doing any new content. We're just going to take what we know up to now and look at how we can apply it to the project coming up as a means of review. Okay, so week 13. If you are presently in Programming Algorithms 2, or you have taken it, or you've used a language like C or C++, then you're going to see hopefully some things that are familiar to you this week. We are going to be doing the assembly version of what we call pointers in high-level programming languages. So what we're talking about and learning this week is how do pointers actually work on the processor. All a pointer is really is an address in memory. Okay, so yeah, I can answer that. So there's a question, which is better, computer engineering, I assume, or computer science? The answer really depends on what your preferences are. So if you prefer to, like if you really like this class and you prefer sort of thinking about how the processor actually works and you imagine designing the circuitry of a processor, in other words, you kind of like the hardware-oriented stuff, then it's probably computer engineering is more to your taste. If you really like making software and programming and creating software systems, then computer science is going to be your better choice probably. So computer engineering is the hardware, which a lot of that would be designing and working on the actual functionality of processors, and computer science is about the software. How can we make software that uses the hardware to solve problems? So hopefully that answers that a little bit. Okay, so week 13. So let me just show you though, week 14. So notice there's just a 14x because I wanted to keep my little numbering scheme, but there's no assignments next week. So when you come and look at next week's module, all you're going to find ultimately is a lecture that I did on Monday morning next week. You're welcome. Okay, so anyway, just note that for the week of Thanksgiving, Butte College is still in session. For this class specifically, we're going to do a review lecture oriented toward applying what we've learned to getting started on the second project. Okay, but for this week, what are we doing? So this week we are doing dynamic memory. This word, malloc, is how people say it in our line of work. Malloc, it means memory allocation or memory allocate. But in the C language, you'll find a malloc if you're doing C++. The C++ form of malloc is new. So that's what we do in C++ when we want to do a malloc. In the C language, we actually do a malloc function, and in HLA, we do a malloc function. But this means allocate memory. And what we're talking about is doing dynamic memory as opposed to static memory. All right, so we're also going to use D-word variables to keep track of our dynamic memory. And then we'll take advantage of what we know about addressing modes to access dynamically allocated memory, manipulate it, print it, those kinds of things. And then we will use the free function or free procedure to let go of our dynamic memory when it's no longer needed. If you're taking C++ right now, free is delete in C++, but in HLA it's called free. Yes, so the question is, does HLA basically allow you to manage memory like C++? And the answer is yes. And the reason that's so is because they're both running, well, in our case, it would be running on an x86 processor. So don't forget that at the end of the day, this is really about how are we interacting with the processor and the memory. So the same functionality that HLA uses to use the processor and the memory is the same functionality that C++ does. Just C++ is designed to make that a little bit more human-friendly, even though it doesn't always feel that way. C++ and other high-level languages are just meant to feel more friendly to humans, whereas HLA is trying to peel back some of the hidden layers and actually show you what the processor and the memory does. You can totally do that. So if you want to you won't run your system out of memory, but you will run your program stack out of memory. So if you want to see that happening, Captain Price, put a malloc inside of a loop and eventually it will fail. In fact, I might do one just to show us that. But a loop is a way to experiment with that. You can't crash your computer anymore because the computer will protect itself. The operating system will prevent that from happening, but you can certainly run out of memory inside of your own program space. Okay, 2 reading sections. Homework as usual. Lab, which I'll come back to. And then, like we've been doing in our class, trying to get you to sort of consider the concepts we're learning in the context of the processor itself, and look at the high-level languages and see how do those things translate into high-level languages. So last week, for example, we did HLA arrays, and then I asked you to look at other programming languages and how they offer array functionality to you. And we got 9 different languages, so that was pretty awesome, out of 15 people. And then the last is a reminder, so homework, lab, and discussion as usual, and then the second project, you should be starting on that sooner than later. After today, technically you pretty much know everything you need to know. Putting it all together you might not be comfortable with yet, but you have all of the tools you need after today to do the second project. You have all of them. Okay, so I'm going to have to switch back and forth a little bit, as I often do, I think, in this class. So first, let's just look at the code, and then I'll draw some pictures to try to explain what's going on. What do you need to see? You need to see VirtualBox. Okay, so let me get logged in and spin up a sample program. Okay, I'm just going to call it Dino. Pleases me to do so. Make sure it goes in the right place. Okay, so what we're adding this week, what's different is we're going to start using dynamic memory instead of static memory. Now, one thing that's awesome about HLA is that the static memory is really easy to see because you declare it as static memory in HLA. You literally use the keyword static. I might spin up a C++ program on the side just to compare and contrast the two. I'm not going to save this code, but we'll have it syntax highlighted. Okay, so let's do static memory. We'll do X, which is an unsate. So in C++, of course, that would look like this. HLA automatically zeroes things out for you. C++ doesn't. Technically, I should say unsigned here. So anyway, this is static memory in C++. This is static memory in the HLA language. What we mean by static is that the memory for that variable is automatically allocated when your program begins to run, and it's automatically released when your program stops. So same thing in C++. This is a static variable, X. It's automatically allocated, that memory, when the program fires up, and it's automatically released when the program shuts down. So that's what we mean by static memory, is that the management of the memory allocation for it is automatic. You don't have to do anything. You just have X, and then magically it's there, and then when the program ends, magically it goes away. Well, sort of, Captain Price. So in C++, if you don't specify an initial value, C++ will just, whatever happens to be where X is what you get. Whereas HLA, when you compile, it automatically zeroes, or when you run it, it zeroes it out for you. So it's not really, I mean, it's more a matter of the fact that C++ just doesn't offer that functionality for free. You have to zero it out manually, whereas in HLA it does it for you. Just a difference in language design. But in both cases, you don't really have any control over where your memory comes from. It just is. Okay, so we're going to add I'm going to call it I'll just call it array and a D word. So D word is a data type in HLA, as we talked about last week. So array is a variable of the type D word. All that really means is array is 32 bits. It's a good choice for memory addresses in HLA, D word is, because it doesn't have a type associated with it. It's just 32 bits of data, which in our class is the size of addresses are 32 bits. So array will be the address of an array in memory that's 32 bits. In C++, we would say, so in C++, we would have to say specifically an address of what. So in HLA, we don't have to say what kind of data goes in the array. It could be a bool array, a char array, an int8 array, an uns32 array. We do the work sort of manually of doing that mapping, but in C++, we would have to say, I want an int array. And also in HLA, it's wise, I mean in C++, it's always wise to initialize things. Yeah, Captain Price has a question. So, in terms of memory allocations, are C++ and HLA the same as and the answer is yes. So their static allocations are the same in terms of the amount of memory, but HLA gives you the extra bit of functionality, which is to zero it out for you. The memory is allocated. It's allocated. It's just a matter of is it initialized? I'll draw some pictures and hopefully that will make that more clear. Okay, so here's in C++. Actually, let me draw a picture now. And so I don't need to save that, but let me switch over and draw a picture now of what's going on in both places. It's the same picture, so that might help. Okay, so what's going on here? So we have RAM, the computer's memory, and assume that this whole thing is RAM. So when we run our program, technically we get a whole bunch of memory set aside for it. And we get things like our variables, we get the stack, we get the executable stuff or the instructions. And so on. And technically we also have a thing called a heap, but I'm going to draw a slightly different picture of it. So when you run a program on an x86 computer, it actually automatically sets aside a whole bunch of memory to contain all of the things that your program needs to run. So it sets aside memory to hold the variables you've declared. It sets aside memory to represent your stack so that you can push and pop on it. It sets aside memory to hold all of your instructions that you want to execute. And then it also has this thing called a heap, but I think it's easier to understand if I draw sort of a more dramatic picture of this thing, which is what I'm going to do. So you run your program, it sets aside a whole bunch of memory for all the stuff that your program is, and when your program is finished running, then it cleans all that stuff up. And all that memory goes back into the pool that the operating system uses to hand out to the applications that are running. Hopefully that makes some kind of sense. Okay, but I'm going to simplify that picture a little bit and just talk about the variables part. So when you run a program, technically the operating system sets aside a whole bunch of memory for all the stuff that's in your program, but let's focus on the variables specifically. So one thing that you get is the static variables, which in our program we have an X and we have an array. Although the array is special. You also get, and this is I think easier to understand conceptually, you also get what we call the heap. This is RAM, but basically, or some people like to call it the free store. So you get memory that is automatically allocated for your variables that you declared. And then you also have this sort of growth space called the heap, where as you need more memory, you can grab it. Or the free store. And this is where the dynamically allocated stuff comes from. Still in RAM. But conceptually, you have static memory, which is automatically created and destroyed for you. You have dynamic memory, which most of us call the heap, which is a place where you can allocate unspecified amounts of memory at runtime. So this is sort of your growth space for adding memory as you discover you need it when a program is running. If you've taken programming algorithms 2, when you make it a linked list, the linked list is all created dynamically in the heap. But here in HLA is all we really need to worry about. So static memory, automatically created, automatically destroyed. The question came up about initialization. So in C++, the memory is allocated, but unless you specify a value, whatever happened to be in that little cell of memory is just what it is. In HLA, it's automatically zeroed out. But not in C++. But in both languages, you get the allocation of memory, you get the heap, where you can add additional memory on the fly or dynamically as you want. The only difference is HLA, for free, zeroes out all these cells of memory, whereas C++ will not unless you specify an initial value. C++ technically probably executes faster for that, but not faster enough that it just seems like a dumb idea. So we've been doing static memory all the way up to now. This week we're going to add dynamic memory. And what we're going to do is mallocs. So when you do a malloc in HLA, you specify how many bytes you need. And when you do a malloc, you get that number of bytes in the heap. So here I'm asking for 10 bytes in the heap. Somewhere in the heap. What you get back from malloc, by the way, is the address on the heap where that memory was allocated for you in EAX. So I do a malloc immediately after. EAX contains the address of this first cell. So what I typically do is I call a malloc for the desired number of bytes, and then I immediately will use move to copy that address to a dword variable in this case. So that now array actually refers to that same cell on the heap. So I literally have the address stored in static memory of dynamically allocated memory. Now if I do another malloc right after that, let's say I malloc 20 this time, then I get 20. That's miserable to write. I get EAX. Now points to the new one. Then I've allocated now 30 total bytes, but 2 separate sort of sections and 2 addresses of where those blocks of memory have been allocated for me. By the way, if I do this, if I overwrite array with this new address, I now have lost access to a block of memory that I allocated, and I can't get back to it. There's a name for this in our line of work, by the way. Does anyone know what it's called when you allocate memory and then you lose your handle on it? It's a leak. Good one, Captain Price. So this code right here, where I allocate 10, store the address, and then I allocate 20 and overwrite that stored address, is called a memory leak. There's no getting this back until the program is shut down. So if you have a program that runs for a long time, web browsers in the past have been guilty of this. They run in the background for hours or days or weeks. they allocate little bits of memory, and somebody makes a mistake and leaves leaks, they eventually start to eat into the performance of your machine a little bit. Good one. So Captain Price has anticipated the next question. So something needs to happen between my first 10 bytes and my second 20 bytes so that I don't cause this leak. And the answer is, that's correct, Captain Price. I have to deallocate or free this memory. So in HLA, it's called free. So, and what you do is you free the base. You just say free and you give it the address of where your block of memory that you want to free is. And it will work out the rest for you. So before I allocate the second 20, I need to free the first 10 so that I don't have a memory leak. So you allocate, you use the memory, and then you free it before you allocate again. Now sometimes you don't actually free before you allocate, but in this case, to avoid a memory leak, I need to make sure and free the original block of memory before I allocate a new one. Okay, so all this stuff that I drew by the heap, which I know has gotten to be just a terrible mess, the challenging part about dynamic memory is that it is your job, the programmer's job, to allocate and free memory. That's our job as programmers. Very, very, very easy to make mistakes, and lots of mistakes are made all the time by programmers everywhere in the world with this issue. They're controlling dynamic memory. They allocate some, they use it for a while, and then they forget to free it, and then get memory leaks, which if you do enough of those over enough amount of time, you can see performance issues crop up on your computer. Okay, so anyway, static, that's all done for you, and that's always the favored way of managing memory. Is static, because you can't make mistakes with static. The system does that for you. Dynamic is powerful because you can grab new memory as needed. You don't have to even know how much memory you need before the program runs, so it's powerful. But it comes with the responsibility that you need to make sure that you let it go when you're done with it. That's correct. So Gersavax asked, so we can just do one malloc and allocate an entire array, and the answer is yes, you can. In fact, that's what you want, because when you do a malloc, you get all of those bytes contiguous. So that's highly desirable that it works that way. When I malloc 10 bytes, I'm guaranteed that those are all contiguous in memory, side by side by side, like an array. So at one time we can just allocate one array before we delete the first allocation. I'm not sure if I'm getting the question, but hopefully I'll address it as we go through examples, Gersavac. So let's see if I answer that question when we go back to code. So when I'm doing malloc and free, I'm working in the heap, which is just free store. It's free memory that's there so that I can allocate it as needed. And then I use it for a while. When I'm done, I can free it, and then I can allocate some more. Static is always better, but in this case I'm not giving you the choice because I want you to have the experience and hopefully gain some insights into dynamic memory. Okay, so in C++, by the way, when we want to do an allocation, we do the keyword new. When we want to do a free, we use the keyword delete. And this is getting just horribly messy. So C++, new is how we allocate memory, and delete is how we free it. But in HLA, to allocate memory, we use malloc. To free memory, we use free. Yes. Okay, so the question is, can we use multiple pointers and get multiple blocks of memory on the heap? And the answer is yes. We can make a whole bunch of pointers, and we can make a whole bunch of allocations that are attached to the different pointers. So yeah, we could have something like this, first of all. So we could, I'll just call them P1, P2, and P3. Static memory, and each one of these could refer to a separate block of dynamically allocated memory on the heap. So yeah, we can totally do that, and then we can gain a whole bunch of separate sections of memory that we have pointers to on the heap. So hopefully that, so you are correct, yeah, and hopefully that sort of answers it. You can. Now there is a limit. It's pretty big, but you can experiment how big it is. So if you do mallocs in a loop, eventually you will run out. And I'll show you in the documentation how we can detect that. But you can have multiple pointers in your program, and you can have those pointing at different blocks of memory that have been dynamically allocated on the heap. Okay, so now let's go back to the machine and see what that looks like. How am I doing on time? I'm doing okay on time, I think. Okay, so I'm going to keep with the C++ one for a little bit, just as a, so if I want 10 dynamic integers in C++, I would say array equals new. That's the keyword in C++ to allocate things. And I would say 10 integers. So what C++ is doing for you that you can't see here is it's automatically scaling to the number of bytes required. So let's say, for example, that integer is 4 bytes. C++ automatically computes for you how many bytes you're actually asking for, which in this case would be 40. So in the end, I get array pointing at the heap where 40 bytes, enough to store 10 integers, have been allocated. And then I can do things like in C++ anyway, I'll just populate it with 1 through 10. So in C++, once I have dynamically allocated memory, if it's behaving like an array, I can just treat it like an array. And then when I'm done with it, I have to tell C++ that I'm dumping, or Captain Price got me with that dump because I like the word. I'm deleting the heap memory associated with the array, and in C++ you have to tell it that it was actually an array's worth of memory so that it can figure out how much to let go. So here's allocating memory, here is freeing memory in C++, and in between I'm using the memory. So let's see what that same thing would look like in HLA. So in HLA, you have to do a lot more of the work manually. What you can't see here is that C++ is computing how many bytes that actually means. In this case, C++ is figuring out the byte scaling for your addressing for you automatically. So C++ makes that whole process a little bit more seamless. So here's that same stuff in C++. Let's assume that these are int32. So in C++, in HLA, how do we get an array of 32? Of 10 int32s. There's two ways to do it. One way is to know that int32s are 4 bytes, and if I want 10 of them, that's 4 times 10, or 40 bytes. Or, I don't use this very much, but you can. HLA has a special size thing, so you can say, give me the size of an int32 and multiply that. So this is a special HLA thing, but you still have to compute the number of bytes. So What's the size in bytes of an int32 times how many int32s do I want? At the end of the day, I can just do that for myself and say that's 40 bytes. That's what it is. Same thing though. So memory allocated. That's this part. Memory allocated. The second part, which is this part in C++. Where do I store the address that this memory allocation got me? That's what this does in C++. Allocate memory, store its address somewhere, that's C++. In HLA, allocate memory, 40 bytes, store the address, EAX from malloc, into a dword variable. So that's the HLA way of doing that line of code. I'm going to put this up here. Messes with my sense of order. Okay, so in C++, those two lines are done in one line. Alright, now let's do the for loop part. Same for loop, except for instead of I, I'm using ECX. And then I'm going to move. Well, let's see, I need to, I don't want to break ECX, so let's move it. Technically, I should be careful. Make absolutely certain that that address is in EAX. Let's put that in EBX, and then let's increment EBX. This part right here is I plus 1. That's all that is. I plus 1. Then we will move I, which is really I plus 1, into address plus the offset times the scale, which in this case is 4 bytes per, since I wanted in 32s. So there's the for loop, this for loop in assembly. Technically this is pointless right now, but I wanted it to be clear that you got to make sure that that address is in EAX for this code to work. Hopefully this is making sense. I equals 0, I less than 10, I plus plus. Because I'm using registers to do the I plus 1 thing, I'm going to use a middleman for that. So I don't want to break the counter, so I'm going to copy I, ECX, into EBX, increment it, add 1, and then copy that into the array. Now remember, in HLA, you need the base address, you need the offset, and you need the scale in bytes, which you're getting all that for free in C++. And then the last thing in HLA is you call free on the address, and the cleanup sort of happens. You don't have to compute how much to clean up, it knows that. You get that for free. So this is me doing a dynamic array in HLA. So I'm going to do something here. I'm going to put this back in a second. I want to point out something to you that makes it harder in HLA. Besides the fact that it just looks a mess, but most of you by now should be used to seeing registers and sort of thinking about what it is that they mean and what they do. But if you look at this program right now, there is no indication of the data type. You have no idea what the data type of this array is. There is no clue whatsoever about the data type here. The only clue you have is that each item in the array must be 4 bytes big. That's the only thing that you know. If you look at this HLA code right now, is that each element of the array is being computed as a 4-byte element. That's the only thing you could possibly figure out here. What the data type is, if that's an int32 or an uns32 or just raw hex data, there's no way to tell. Just pointing that out, that makes HLA harder. Whereas in C++, it's pretty obvious that your dynamic memory is meant to be referring to signed integers. That's a huge advantage of high-level languages, at least the strongly typed ones where you know the data types. That's a huge advantage to be able to look at the code and know what data type you're talking about. In the assembly world, you don't always know the data type unless someone has documented it for you somewhere to tell you what in the hay is going on. We don't know. Just a fact of the matter here, so be careful about that. If you have to, put comments for yourself. Okay, so that's the basics. The whole critical stuff here is the malloc. We allocate 40 bytes of memory, and the free, which is to free the memory. The way we use the memory is just like the arrays we've been doing. So the stuff in between doesn't change. If we allocated enough for an array, then we can code it like it's an array. The only difference is we have to manually allocate it and manually free it. And that we weren't doing before. Yeah, so Captain Price pointed out so each element is 32 bits, yeah. But you don't know 32 bits of what, right? You don't know if it's 32 bits of unsigned, signed, if it's 32 bits of just raw hex data for whatever reason, if it's 32 bits of addresses to other things. That's tricky in HLA and assembly programming because if someone didn't leave you notes or comments in the code to tell you what's going on, that can be hard to figure out. But you're right. This is an array of, we can tell from this spot right here, it's an array of what must be 4-byte or 32-bit items of some sort. Eventually, probably someone you'd find in an actual program, a typecast that would give you a clue, but as this code is written, there's no way to know. Okay, that's that. I think I can get rid of the C++ one. I'm probably going to bring up the lab. So the big shift is that we are going from the static thing that we did last week. If we had this array done statically, that would mean it'd be in the automatic memory, and we wouldn't need this or this. We would have to change this to say address of, and we wouldn't need this. So if we had a static array, we wouldn't need malloc, we wouldn't need free, and we'd have to derive the address of the array slightly differently. But the switch is that we are moving over to dynamic memory, which means that our variable just becomes a pointer, a D word, a pointer to the heap. Okay, hopefully that's okay for the malloc and free stuff. It's arrays. Project 2 is arrays, that's it. They're dynamic arrays, which is not a big deal. The hardest problems are in the working with the arrays parts, not with the dynamic parts. The dynamic parts are easy if you remember that everything is in bytes in HLA and assembly. You have to figure out how many bytes things are. But otherwise, the hard stuff is actually writing the code to use the arrays, the heap arrays themselves. But it's no different than static arrays. Okay, so here we go. Let's get the lab and get a start on it. Yeah, I'm doing okay on time. I will show you where I'm going. So I'm going to go to the lab page and go grab the code. Now I happen to like this stuff. I like the feeling that I'm like fully in control. The downside to be fully in control is that if it's easier to make mistakes. So if a mistake is made, that's on me. Which means that I need to think, I need to pay attention to what I'm doing, I need to test my software a lot to make sure that things are working. What am I doing? Oh, switching. So I grabbed the code. I'm going to switch the view. I'm going to go paste it into my virtual machine. So here it is. Get rid of you. Save you. Make a new one. Okay, so let's look at Lab 12, 13. See what it's asking of us. The point, obviously, is to have you use malloc and free inside of a program, but also to pay attention to the other stuff that's going on. So someone made a really smart post last week that said, my outputs look wrong. What's the problem? And then one of your classmates answered, I think you didn't do the right data types. So several of you just did sloppy work on the lab, so you will have been deducted points, but what you should do, instead of just sort of barf this stuff out and say, done with it, test the program. Like your classmate did, who went and made a post in Piazza that said, this can't be right, my output looks like crud, and they figured out what was wrong and fixed the problem. So you should run these programs, not just compile them like, oh, it must be done, I don't even know what's going on inside, but if you want to do what we do as computer scientists, you need to take time to actually study what's going on. I've written almost all these programs for you, and I'm sort of admonishing you now, but part of the point is because that should leave you some space in your mind to run the program several times and experiment with it. What happens if I change this little thing? What happens if I do this input? If you are just sort of doing the bare minimum and calling that good enough, you will not make it in our line of work. Because no one will hire you because you will have crappy skills. So if you want to develop good skills, do what your classmates did who got 100% on last week's lab. Don't just stop with compiling it, run it, look at the outputs, think about the outputs. If they don't make sense, get on Piazza and see what the problem is and fix it. Otherwise, you will have just spent a bunch of time and some money not developing skills, and that would be kind of a bummer. So anyway, there's my admonishment. If we were face-to-face, those of you who've had class with me get a lot more of those, but if you didn't get perfect credit on Lab 12, it's because you did bad work, which means you didn't take any time to compile your program, run your program, test your program, think about what it's doing. If you got 100% on Lab 12, then you kicked ass, and you should be, hopefully you're being rewarded with a increase in your skill set. Anyway, that's enough of that. But there's only 8 things in this lab, so study this lab. This is a lot of stuff that you need for the project. So let's look at this code. Right here at the top, there's a variable called numbers. It's a D word, so I'm just telling you right off the bat. This is a pointer, which means that this thing is going to store an address in memory that has been allocated with malloc dynamically. This size is going to be used to track how many cells of memory were created. So this is effectively an array address. This is effectively how many elements are in the array. Now we're going to have to look for the clues in the code for what kind of array does this program build for us, because it does. Okay, so pointer, It's going to be an array address. Size, how many elements are in the array, because we need that for things like printing and whatnot. Okay, get in 16. You've seen that one before, but if you don't know what these are doing, please take the time to study them. You need this procedure in project 2. Get uns 32 has also been done for us. It will be handy for you in project 2, so if you know what it does, that can be helpful. Go again, you've seen 1,000 times, so nothing new there, but you can probably use some adaptation of it on the second project. Okay, so print. So this print procedure, and I mean, I'm sort of, I guess, touting my own programming design, but this print procedure should function without reference to anything outside of it. So it should make reference to nothing that's not in the procedure. So if this procedure cannot function without this address, which should be a pointer into memory, this size, which should say a number of elements in an array, then something's wrong. And in here we're going to write a for loop that prints the contents of the array, but I want you to notice we don't know what kind of array it is yet, so we're going to have to read the code and figure that out. Well, how do I know what kind of array it is? We don't yet, so we're going to have to keep reading the code and find that. Eventually, though, once we find out what kind of elements are in the array, then we can write this for loop. Okay, here's another procedure, edit cell. You've seen this one before, except for this one's a little bit simpler than last week. It should be able to function without any reference to anything that's outside of it. So it has as its own parameter a pointer, has its own parameter a size, and then it's actually already doing the work for us of using the size. Is it? Yeah, it's complete, except for I did a crappy job of the tabs for some reason. So let's see if we can get any clues in here that are useful. Actually, I'm going to make you guys do this on the broadcast. So it's pushing all of the double word registers, so we don't have to worry about wrecking anybody's registers, popping them all. All right, so we're loading the size into ECX and then decrementing it. So the size being the number of elements in the array, decrementing that to be one less. So the first question I'll have for you is, if you look at those 3 lines, this is a challenging one, but why are we decrementing ECX here? This is a tough question. Everything you need to know is in those 3 lines. We have a size, which is a number of elements in the array that we put in ECX, we decrement it, and then we use it on this line. So why are we decrementing it? It's a good guess, but nope, not quite right. So let's think about it. Has something to do with the size, which is a number of elements in an array. So for some reason, we're copying the number of elements in an array into a register and then decrementing it, which means remove it by 1, subtract 1. And then we're using it in this get. Okay. Yeah, so because the array starts at 0, so when we do a get uns 32, we want, and notice it says enter the index of the item, so we need a number between 0 and not the number of items, but let's say the items are 10, what's the range of indices? So if this size is 10, what's the minimum and maximum range of indexes? 0 to 9. Good one, Glazer. Okay, so those 3 lines, if the array has 10 elements in it, then the only valid index values are 0 through 9. That's why we do that. So that's what that's about. So now look what happens. So we get an index, a zero-based index, and then we copy that index into ECX. So this is the index, the zero-based index of the element they want to edit. There you go. Good on Captain Price. So yeah, we decrement so that we guarantee that we get a proper maximum range from 0 to 1 less than the size. And then we copy their input, so they're going to select, let's say, 0 through 9 for a size 10 array. So now we have the desired index in ECX. Now we move the base address into EBX, which is why down here we have EBX, ECX, so base plus an index times the scale. So Captain Price asked if we were to try to access the memory at an invalid place, it should crash. It's not a guarantee it'll crash. You kind of hope that it will crash. But if you try to access memory at an invalid location, you'll either get bad data or you'll get a crash. So, or you introduce bad data into some other part of your program. It's a great question, Captain Price. If we're not careful about this index here, kind of all bets are off in HLA. What you actually want as a programmer in that case is for the system to crash. Because if the system does crash, then you know there's a problem. If it doesn't crash, then you may not detect the problem until bad data comes in somewhere. And you're like, how did that bad data get there? And it can be very difficult to hunt down. So it's a good question to ask. Like, what happens if we bung this up? In HLA or assembly, you don't know for sure. You get lucky if it crashes, and if you're unlucky, then you get bad data inserted somewhere. It's not fun to break. Well, yeah, I guess you could say it's fun to break programs. It is the work, though. Half the work of teaching programming is breaking people's software. Although more as they get more advanced, right? So you guys, that's a lot of what I do with your software is try to break it, of course, because you're more advanced. Okay, so we get a good index in ECX, we get a base in EBX, and then we can tell from this line of code that our cells are 2 bytes apiece. So it's these 2 lines that tell us what kind of data this array is, even though it would have been nice to have it documented, but we had to do detective work. So what is our array? We can tell now what the array has in it. And it's one array type for the whole program. So what kind of data is in the array in this specific program? It's somewhere in those 2 lines that you can find the clue. $16 bits. So I think you meant 16 bits. That's correct. Good one. All right. So Captain Price narrowed it. So they are signed integers. They're 16 bits. And then Captain Price, they are signed 16-bit integers. And Captain Price could tell that because the line above is getting an int 16. So it's calling a function that returns an int 16 and then immediately returning or copying that int 16 into the array. So once we get down to these 2 lines, we know, oh, okay, in this program, we're talking about int 16. Right, not un16, int 16. So lab 13 is an int 16 array. They are 2 bytes a pop. So let's go write ourselves this loop with that information that we have. Int 16. I don't know why the tabs are messed up sometimes. I must have edited it on my Linux machine and the tabs got messed up. Okay, so this procedure is printing int 16. Got the base loaded up. So 4, move, 0, 0. So we're going to use the size parameter. And as long as one of these is a register, then we're allowed to compare them. So as long as ECX is less than the size, so there's a loop that starts at 0 and goes for the number of elements in the array. It's just like an int I. Not less than or equal to, so what happens if we do less than or equal to? Breaks it, that's correct. So on a size 10 array, this would go from 0 to 10, which is 1 too many. So on a size 10 array, we want to stop one short, 0 to 9. That's right. Something to be careful of, and I'm glad you're pointing those things out, because it's a super easy mistake to make, is to put less than or equal there. Starting from 0, you went 1 too many. So this will go from 0 to 9 because of the way that logic works. Hold on, let me block somebody. Okay, so there's the loop, looping for the size of the array. So you're going to need this kind of loop in the second project. And what are we doing? Oh, just printing the contents of the array with the space. A new line at the end. Well, that part's easy because I'll just wait until after the loop and print a new line, and that's the end. Okay, so how do we print out put a space after each one? So the question is, what goes in here? Let's start with the memory part. So does anyone want to venture what goes in the square brackets there on line 94 for printing out an element of the array? That's correct. So the array is 16-bit elements of an unknown size, but we know the size because we have a parameter for it. So that's all we really need, is to have access to the size, and then we can control this loop. And we know they're int 16 specifically, which is going to be important. But let's deal first with, okay, so let's just increment one at a time and see if we can use scaling instead, Captain Price. So let's use the index counter and scaling. Instead of adding 2, let's just use scaling. So what goes in here? Okay, EBX, that's the base, plus, so you're close. So this is the right scale for int 16, that's the right base. What goes in here is good one, ECX. So probably your fingers. So good one, Gersava. The base, which we had from here. The index, which we're producing as an int I equals 0 kind of thing in the loop. And then the scale of each we know is 2 bytes because they're int 16. So now how do I make these things? This is going to print as hex unless I typecast. So to make it print as decimal, I also need to typecast. And what's the type? Good one, Captain Price. Int 16. All right, so you guys are on top of it. You're doing really good. This stuff ain't easy. It's not easy. That's a mess. So you really have to stop and think about all the bits and pieces. So I have to look for my base. I have to look for my index. I have to know the scale, and I have to know the right type so that I can do a typecast and make it look pretty on the screen. In this case, look like a signed 16-bit integer. That's the whole loop. Yeah, it is. I agree, Captain Price. I think, like a lot of us think, just the purposely repeating the same concepts is useful, especially because some of them are pretty complicated. Okay. So I wanted to show you the whole detective job. We found by reading down, we finally found in the edit cell procedure that we could sort of figure out what the data type of the array was, which allowed us to scroll back up and do the for loop and the new line with a space after each one. Okay, so what's number 3 here? That one you know how to do. This address parameter, the address parameter, copy into EBX. Ooh, that's tough. I guess we'll do this one together. Do I have time? Ooh, I'm run over. We're going to have to do the whole thing together, so if you got to bow out, it's okay. I'll put the video up after we're done, but I'm going to go ahead and finish the thought because this one's harder than normal. Okay, so this is a procedure to find the maximum value inside of an array, and do we return it? Yep, we put it in AX. Okay, so let's do that. See, all the tabs are messed up. This procedure you need on the second project. If you can do this one, then you can find the minimum value in an array, so that should be super, super handy. Good one, Captain Price. So move address to EBX. So we take this address, the parameter, and we copy that address into EBX. We do that because that's the only way to work with the addresses in terms of dereferencing them. Okay, so copy the first element of the array into AX. So something goes into AX. That's close, Captain Price. So conceptually, that's correct. We move element 0, but we don't have an array. We just have an address, right? So we have an address. So to access that memory, we're going to have to dereference it. Start at a base, go to an index, and use an appropriate scale. So what's the index for the first value? Well, what's ECX? So let's do something with ECX so that your idea works better, Captain Price. No, keep going with the thought, Captain Price. You're on. You're correct. We need ECX to be something. So you already said it. Not 2. So base plus the index of the element we want times the scale of each element. So the base, what's the index of the first, the 0? Good one, Gersova. 0. So we'd move 0 to ECX, and then this would give us the first element. Now if you're super clever, what is 0 times 2? It's 0. So technically, since 0 times 2 is 0, and we're really saying EBX plus 0, you don't even need to do that stuff. So the address of the array is at the very same time the address of the element. Kind of cool, isn't it? Now once we get inside the array, that's going to have to change, but for the first element, since the index is 0, and we multiply that by the scale, well, we end up just getting 0. So this is the address of we call it the base address of the array, but at the same time, it's the address of the first element. So that's what it is. Yep, since it's the first element, all the rest of that stuff becomes 0 anyway. So if we just grab the address, we get. Now you can, if you want to, typecast this, if you feel uneasy without the typecast. But if you grab 1 in 16 at the base, you get the first one. Which is kind of cool. Technically, you don't need the typecast because it'll just grab 16. But if in doubt, typecast. So that's kind of crazy, and it's easy to lose track of what that is. So if you're watching the video later, go back and go slow over that part we just did together. The people in chat are sort of right in the middle and engaged in it, but if you're watching it on video, you may want to repeat this part we just did. So anyway, hopefully everyone got why we could eliminate the ECX times 2, because that was really just eliminating a 0. Okay, so what does AX have in it? The first element of the array. What's its value? We have no idea. Whatever it is. Okay, so now we're going to use a for loop, and we're going to look at the remaining values to see if there's any bigger ones. Okay, so a for loop. We already did the element at the first index, so we're just going to start right at the first one over. We already did element 0, so now we're going to start at element 1. Go all the way to the end. Hold on, I gotta fix the tabs. It just looks so terrible. Okay, so we're going to look through the rest of the array. We're looking to see if we can find something bigger than that. They're 2 bytes per, so we're going to Captain Price. So when we're looping, we need to remember to scale when we access memory. So we're going to move the index one at a time, but we'll scale by 2 to make sure that we get the right data. Okay, so our job here is basically to see if there is a value that's greater than AX, which was the first one that we grabbed. So this loop's job is to allow us to look through the remaining elements. We already grabbed the first one and put it in AX, and we're going to look through the remaining elements to see if there's a bigger one. So we're always comparing against AX. Is there something that's greater than it? Because we want to find the biggest one in the array. So the question is, there you go. So EBX, that's the base, plus the index times the scale. There's where we get the 2 byte bit. That's for the remaining ones. Now you're going to, this one, if in doubt, but in this case probably you do need to typecast it. So we're going to access that one N16 in memory and compare it with that one. If it's bigger, then we're going to move it. So if that element is bigger than AX, then we're going to move that element into AX. So as we're moving across the list, every bigger value becomes AX. Oh, that one's bigger, that's AX. Oh, that one's bigger than the last AX, that one's AX. This is called a greedy algorithm in computer science, where basically we take the first one and then we look through all the rest to see if we can find anything that's bigger. Every time we find one that's bigger, then we work against that one as being the biggest and then keep going. So when this algorithm is done, AX has the biggest value in it. It's pretty cool. You can do the same thing for the min on project 2. That's and it is, yeah, so Captain Price, I bet you've seen this algorithm many times. So and a lot of you will have seen this algorithm more than once. Okay, so we don't know where that's being used, but that should in theory. If in doubt, and I'm probably no one in here in chat is, I think all of you probably got full credit on the last lab, but if you're watching the video later, or if you're not in the habit of testing your program, this one you need to test. If you put data in your array when you run the program and the maximum doesn't print the maximum, something's wrong. So this one needs to be tested by compiling and running the program. Okay. Create array. So this one kind of tells you already what we need to do. the tabbing thing. Yeah, I knew it was going to do that. Hold on, I'm just prettying up the tabs before we continue on with this. Just looks so terrible. Okay, so number 5. Well, no, you're right, Captain Price. If this procedure runs on its own, it's going to create a memory leak. So somewhere in here, there better be the free that goes with this. But on its own, you're totally correct. This procedure, if you just run it, it's going to cause a memory leak because it doesn't free any memory. But we'll come upon the free later. Okay, so we need to compute EAX. And let's just do this the quick way. So, does anyone know the what instruction goes here? Oh yeah. The stack will. You're right. Take care of that problem. Okay, what's the instruction for number 5? Not yet. So we need to do this first. So this instruction is not allocating yet. It's just computing. But you're right, Tyler. It is multiplication, but what does that look like in code, in assembly? We're not doing the malloc yet. We're just computing a number of bytes. Mul, good one, Glazer. It's mul. So if you look at these 3 lines, you ask your user, how many elements do you want? The way it's designed, they can't pick more than 10 because it would just cause pain for testing to do more than 10. So they can pick up to 10 elements. And then what we're computing here is the number of bytes that we're going to need to allocate. So if we know our array is int 16s, that's 2 bytes per. The number of elements is in EAX. So if they said I want 10 elements and they are 2 bytes apiece, then I know that I need 20 bytes. So this output should, if they were to pick 10, say I'm about to allocate 20 bytes for you. Okay, now let's go back. Now, we want to allocate the number of bytes that we computed in EAX. So now the instruction is what? To do the actual allocation. Malloc. Good one, Glazer. This is the malloc. So this stuff up here is all about computing the number of bytes that we want. And then we print out a confirmation message like you're about to get 20 bytes. And then we allocate the memory for it. Good one, Tyler. Malloc. Okay, so we allocate the memory. Now what this procedure does, it allocates the specified number of bytes, and then it's going to overwrite EAX with the address where those bytes are. So the last step is to copy the allocated bytes into a variable that's used to store that address long term. So I'll give you a hint. I'm on line 188. So the long term storage is one of these. So one of these is meant to hold the address of the allocated array or a pointer to it. 188 I was on? 188. So the second argument is going to be our pointer where we're going to track that memory address. Good one, Tyler. So we take the address that malloc came back with. So we give it a number of bytes in EAX, but it comes back with the address in EAX. And then we copy that to our variable numbers for long-term storage. So when this procedure is done, we have allocated the number of cells they want, scaled to the number of bytes per cell. So if they say I want 5 integers, they're going to get 10 bytes. So it'll say allocating 10 bytes in that example. And we allocate the 10 bytes, we get back EAX, and we copy that pointer, that address, into our numbers variable. So that's the whole create array procedure. We're almost done. Yeah, we're almost done. It would be 10. So it would be 10 bytes. If they say they want 5 integers, then they're going to get 10 bytes because they're 2 bytes per. If they say they want 10, so remember on the create, you ask them how many elements do you want, and then you scale that by the number of bytes per element. So if they say they want 3 items in their array, that's actually 6 bytes. 3 elements, 2 bytes per element is 6 bytes. Last one, number 8. How do we get rid of that stuff? So number 8 is where we prevent the memory leak, where we clean up the memory. Free numbers, good one, Glazer. So memory leak handled as long as they call delete array. So there's number 8, is using the free. So let's see how the program runs, and then you're going to want to test this since we did all the programming already. So it's going to call create array, which is going to ask you how many elements you want, and then automatically compute how many bytes that is, and automatically allocate the memory for that number of bytes. Your user only knows, oh, I wanted 10 integers. Your program knows that 10 integers is 20 bytes. Yeah, in theory, if you ask for more memory, it might take a little bit longer. You can. Can I create a delay that prints dots? Yeah, I'll show you where to find that, Captain Price, in the standard library stuff. So we'll go look at that up in just a second. Okay, so create array, couple of new lines. Then it calls the edit array procedure, so you can populate the array with data. You're going to want to do that because you want to edit the array with data so that you can then later see if your max algorithm actually worked. So when you're running the program, edit the array, put stuff in there and mix the data around, paying attention to which one is the biggest value. Then your program is going to print it, which should print all of the values you entered. Then it's going to compute the maximum value and print it out. So that's your big test, right? Does that work? Then it frees the memory, and then it asks you if you want to go again and start the entire process over. Okay, so Captain Price is, I'll show you a couple of examples. So, oh yeah, this probably, you're right, Tyler. I think how do I prompt the user for press enter to continue probably is there. Let me switch views and this will close it out. So we're kind of into bonus content if you're getting tired of me. I'm going to do 2 things. So I'm going to go to Piazza. Oh yeah, so it's here. It's in case you guys might want to know too. Can I edit this as the power user? To note, I'm going to convert it to a note, but can I edit it? Anyway, there is. It's in case you guys might want to know too, although I don't think I can. Darn it, I can't change it. Wait, yeah, I can. Oh no, that's just me. Sorry, never mind. Anyway, so the question about how do you do a press enter to continue is here. It's under this, I converted it to a note. It's under, it's called in case you guys might want to know too. So let's go look at the pause real quick. So HLA standard library. I believe that there's a pause in here, Captain. Oh yeah, I forgot to switch your view. Sorry. So anyway, go back to Piazza. So there's a note in here. Says, in case you guys might want to know too. I wish I could retitle that somehow, but I can't figure out how to title it. Reading those flags. Anyway, in case you guys might want to know too, has this sequence of code in it. Okay, so the question about can I sort of fake a pause, and I believe that you can. Timer. I bet it's in timer. So I went to, okay, let me show you what I Googled. I Googled HLA Standard Library. The discussion is, in case you guys might want to know too, which I don't know how to change that. It won't let me edit it. I can only edit my, wait, can I edit the whole thing? Oh, I can. Okay, here we go. Aha. I will put that under MISC and Project 2. Okay, there you go. How to. Press enter to continue. I should have made a how-to label. Well, anyway. Okay, so there's that. Now, I Googled HLA Standard Library for the other thing. And the first link takes you to the reference manual, and I think it's in the timer class. So it's way down here on item 36, way down here. The timer class. And I think that there might be a pause in here. Nope. There's not a pause there. I think that there may be though. Let's look under console. I'm going to do a search for the keyword pause in the whole document and see if I can find it. I think there is a pause. Oh, wait. Maybe it's an OS. Oh, maybe it is delay. Aha! Good one, Captain Price. So I did Control F and search delaying program execution, os.sleep, and then you give it a number of seconds. This says D word. That just really means it needs to be limited to 32 bits. I think it's in seconds. Yeah, it's just in seconds. Oh, look. Here's M sleep. So the other one is milliseconds sleep. So this one is a milliseconds, M sleep, and sleep is a seconds. So you have both options. So try that out. Anyway, maybe I'll if I remember, I'm curious to know if it works for you. So, if you try it out, hopefully I'll remember to ask you. But if I don't, and you have tried it out and it was awesome, maybe you can let us know next week. That'd be cool. Okay. Yeah. So I need to close down. I've asked a lot of your day. I hope it was productive to do the long walk through the lab. That's a key lab for understanding how to do the project. So remember, next week there is no new content. We are going to be reviewing what we already know with an eye toward applying it to solving the second individual project. So if you're with me next week during the broadcast as Monday on normal, or if you watch the video next week, hopefully you'll have a lot of what you need to get a really good start on the second project. Yeah, I think it'd be cool, Captain Price. So try it out. Let us know if it works. That'd be cool as hey. If you're willing to, you could share a note on Piazza, and I'll go in there and steal your code and try it for myself. Okay, I got to run. Thanks a bunch for sticking it out to the end. I hope it was worth your while, at least for solving these problems. Hope you have a nice week, and we'll see you on Monday next week, except for the PNA 2 people who have to see me again tomorrow night. So anyway, have a good day, have a great week, and see you next Monday.